Lab 5, Magnetic Braking with Farday by Anna Catherine Brewer. Introduction. The purpose of this lab is to collect data of a magnet falling through a tube of aluminum foil and to model the interaction computationally. The main result of this lab will be comparing my computational predictions to the observed data. Physics models and concepts. In this lab, I will be utilizing magnetic flux, Faraday's law, Lenz's law, magnetic field on a dipole, magnetic force created on a wire, and the EMF created by a moving bar magnet. To the right is a representation of magnetic flux, in the middle is a representation of Lenz's law, and on the left-hand side of the screen is a representation of Faraday's law. Now moving on to the experiment. Step 1. I used the magnetometer app to mark the north pole of the magnet. Then I positioned the bar magnet just above the opening of the tube of aluminum foil. Then I recorded myself dropping the magnet through the tube multiple times. And lastly, I calculated the average time it took for the magnet to fall through the tube. I interpreted the bar magnet as the system and the tube as well as gravity for the surroundings. So for my initial conditions, I found that the length of the tube was 0.3 meters, the width was 0.015 meters, and that the inner radius of the tube was 0.02 meters. For the magnet, I found that its mass was 0.023 kilograms, and it had a dipole moment of 2.85. Now for the results, I have a graph displaying the fall times for the magnet in each trial on the right-hand side of the screen, and the average time for all 5 trials was 1.66 seconds. Here's a picture of my code, and here's what that code outputted into GlowScript. It predicted that the average fall time would be 2.513 seconds. Interpreting the simulation part 1. So on the previous slide, which color corresponds to a clockwise current and which one corresponds to counterclockwise? The red corresponds to clockwise and the blue corresponds to counterclockwise. How do I know this? Well, because magnetic flux is increasing in the downward direction because the magnetic field is pointing downward because the north end of the magnet is facing the tube. Therefore, the induced current flows in the counterclockwise direction, and thus the blue circle represents this induced current. Interpreting the simulation part 2. So what happens to the dynamics of the system if I flip the magnet around? The south end of the magnet would be pointing into the tube, and the induced current would reverse directions. It would now be moving in the clockwise direction, but the magnet's movement would remain the same. Interpreting the simulation part 3. So how does the total time in tube of my real-world system compare to that of the computational system? How might the computational system be made more accurate? Well, the experimental time was 1 second faster than the computational time. To make the computational system more accurate, I could account for outside magnetic fields that likely played a role in the real-life experiment. This also explains any possible sources of error I encountered in this lab. Interpreting the simulation part 4. So what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Well, when the slope is less than 0, the net force is only impacted by the gravitational force, but when the slope is equal to 0, the net force is impacted by both the gravitational force and the magnetic force. Concluding thoughts. So, what if the resistivity of the conductor were reduced to as close as possible to 0? How would the dynamics of the falling magnet change? Well, lower resistivity means an increased current, which means an increased magnetic field, which also means an increased fall time. And then, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, incomplete rings would lead to less current through each ring, and holes or slots in the tube would therefore lead to a decreased fall time. Thank you for listening to my presentation, and here's the link to my GlowScript code.